get out of my face. Sorry. God. All right, this is when Alex is going to do lots of editing for us. Okay, with all that said, it's Monday. And it's lecture, which means it's time for a new topic. Woo! Streams. Streams are cool. Well, okay. Streams are a data structure. What other data structures have we seen? Good. We see anything else that resembles a data structure? Trees. Queues. Okay. Stacks. Okay, good. We've seen lots and lots of data structures. Streams are another data structure. And we can think of streams as delayed lists. Okay. So, which this means is that we don't compute elements until we need them. This gives us the very powerful ability to do something called infinite streams. Okay, we can create an infinite data structure now because we're not actually going to compute it until we actually ask for the data. So we can write recursive data structures calling themselves, and it'll be great because we can just do that sort of thing. But we'll get there. Now we're going to do finite stuff. To talk about constructors, for lists and for streams. So what's the constructor for a list? Cons. Or you could think of that as, we could also say list, but we're consing onto nil is what it comes down to. Streams, we have constream. How about that? That's a nice abstraction sort of thing. Okay, so constream is a special form, and we'll talk about its definition in a few minutes. For selectors, on lists we have car and coder. And for streams, well, you would think it would go car stream. It actually goes stream car and stream coder. One would think that you would be consistent. However, we are not, unfortunately. But they both have car and coder in them. Okay, so the empty item in a list is called nil. And in streams is called, well, it's actually called the empty stream. And it would have been nice, actually, at some point if the book had defined the empty list as its partner here, but it's not. And in fact, in our implementation, the empty stream is set to be nil. But that's not guaranteed. And our test for empty on lists would be null. And for streams would be, well, you'd think it might be stream null, but it's actually going to be null stream. Why? Who knows? So these two go in front, these two go in back. Huh? Oh, did I do it wrong? Oh, it is stream null. Sorry. Stream null. Old notes, new notes. Sorry. Changed. Okay, so the only one that's wrong is cons. Well, anyways. Stream null, null, stream null, empty stream, nil. Okay, so this is how we can actually build up streams. You can think of them as sort of being lists. So we could write code for streams that will be analogous to the code that we've written for lists. So we wrote a procedure called nth. Nth took a list and a number n, and it returned the nth element of the list. Okay, so now we're going to write stream ref. In fact, nth, which we wrote in class, you could think of, not just think of it, there is a scheme procedure called list ref. It's analogous to stream ref. And list ref will start counting, will return the nth element. So you say list ref, the list, and then the element that you want. So stream ref stream in n is going to do the same thing, except this time instead of the list, it's going to be of the stream. Stream is going to start counting from 0. So we're going to define stream ref of S and N, and yeah. Okay, and this is going to be cond stream null. So if we have a null stream, what should we return? The empty stream, right? We have nothing. There's no element to return. Okay, so this is just like when we were writing list procedures, cons, null, list, nil. Except now we're saying stream null s, empty stream. Okay, next, n is our counter, and I said we're going to start at we're going to have n0. So we're going to test for n0. And if we have reached the end of counting down, what do we want to return? The car. So we say stream car s. And if n hasn't reached 0, what do we want to do? Stream ref on the stream footer. And we can decrement n. Might be one extra. Okay. So, any questions on how? Does this look a lot like the list stuff, but with different names? Yeah, looks a lot like the list, different names. Now we can write stream map. Actually, one point about this procedure here, and that note is on your handout for today. This is different than what the book is doing. The book doesn't check this. And the book should check that. It doesn't. So this code is different than the book has. They're assuming on the book that this will only be called on an infinite stream, and that's not a good assumption to make right now. Okay, so we're going to stream map a procedure over our stream, which is going to be analogous to which procedure for lists? Map. How about that? Hint. Map. All right, so what do we want to do a mapping? Right, we're going to check for the null stream again. So stream null s. If it is null, return the empty stream. Okay. What if it's not null? Do we need to do any sort of test? N equals 0 or anything like that? No. Right? So otherwise, what are we going to do? Con stream, right? We need to build up our stream again. With the first element being what? Right. The procedure applied to the car of the stream, or the stream car. Okay. Stream car and stream coder. You can't do any extra A's or D's or anything like that, but you should need to. Procedure. Okay, so what are we doing for the rest of the stream? So the first element, we've applied the procedure to it.
Just a tangent. I think the other day I heard with the set car bang and set coder bang that you couldn't add the extra D's or extra A's. Is that true?
Right, yeah. So basically, if you're going to do a set car bang, so let's say we have some list. And let's say it points down to a list here. And we want to change this. So here's our list. So this is going to be this cell here. Well, that's the car of the car of the cooter of X, right? So take the cooter, take the car, take the car. So to write the set bang on that, you would say set car bang of the scatter of X to whatever value we want. So we would pick out everything but this one would be where we would change it. And similarly, if we were trying to change this pointer, which would be the CDADR, that would be the set cooter bang of the CADR of X to whatever value we're setting it to. Okay. Yeah.
Just to remind myself, if you had done set bang of the catter, that would have been wrong, right?
Right. Set bang is not going to work on list structure. You need to use the set car bang or the set cooter bang for list structures. Unless you were set banging this name up here to point to something else, right?
That's the only way. Anything within the list.
Within the list, you should be using set car bang or set cooter bang.
There's a variable in the list. Can you set bang the variable and then...
Well, remember, if there's a variable in the list, the way that scheme works is that when we build up that list, we will have already evaluated that variable. So it won't actually be the variable, it'll be its value. So we can't actually set bang within the list because it's already been evaluated to its value there. So that's why we set car bang or set cooter bang. Any more on that stuff? Huh? We don't have to go back to the lecture. Well, it would be nice to go back to the lecture at some point, but if there are more questions there, we can answer them. That's fine.
What's going into the stream? What are we going to put in this data structure?
Numbers, symbols, whatever we want. Procedures?
That's what we're looking for. We're moving
No.
towards.
Well, I said procedures with a smile just because of yesterday's exam, because we had procedures being part of the list.
There's nothing delayed yet about this.
Well, streams are delayed, but we haven't actually talked about the implementation yet of these. We haven't talked about how we delay or anything like that. I just wanted first to show how streams are fairly similar to lists, and then talk about how they're different.
Now, we could have variables in the stream, unlike the list, because we're not evaluating the elements of the stream until we need them. Or is that not true?
There could be variables. They're not evaluated until we need them, but once we need them, they are evaluated. And we'll talk about that in a few minutes, too. Other questions? All right, so otherwise, we constrain the procedure applied to the car to what? Right, recursive call the stream map. So stream map, the procedure over stream cooter. 1, 2. Okay. Okay, so there are a couple of procedures, and actually on your handout you also have stream for each, which will apply something to each element of a stream and print out the result or do whatever the result is. Basically, stream for each is very similar to stream map, except that it doesn't rebuild up a stream. It's just going to apply it to each element of the stream.
What does it do with them? I mean, it applies.
It'll just print out the values, or it could. And actually, if you look at the stream for each, and the next code on your handout is for displaying a stream, and that uses stream for each. So basically, what we can do is, in order to print a stream, we can go over each element of the stream saying, print it out. So we can just print out a stream that way. I'd like to point out that that code right there for printing a stream should not be used on an infinite list. Don't want to do that. If you do that, the way to get out of it, if you guys haven't figured out with infinite loops yet, is Control-C. Control-C, Control-C to break out of your loops. And you can hit it even more times if you want. You're feeling really urgent, but it will start filling up your buffer awfully quickly, and it's not going to end if it's an infinite stream.
You could do that with any of the mapping routines, right? Like the stream map, if your procedure was to take the snapshot or to print out the element would work, right? It would print out the whole list. It's just that you'd also have this return value that you didn't.
Right, but have a return value. Right, it cons back up some stream because you're consing. It's a little bit odd to think about consing up a result of printing something, because you're basically consing up a result of unspecified return values, which isn't exactly what we want to do. So that's why we would, huh? You can do printout. Wait, we could do printout, but it's going to be sort of weird. All right, so it's a little bit neater to not cons that stream back up for it.
Can you think of any other examples of what we might use the stream for each for? I mean, the printout makes complete sense, but I can't think of anything else where we would use the stream for each, rather than the map, or the stream map.
Let's see. We wanted
Asking your ogre to hunt each element in the stream, kind of thing. Like,
right, but you're not building anything back up.
a bunch of that on the last. All you care about is applying a certain procedure to each element in the list, and you're not worried about the return value.
Okay.
Side effects.
You don't want to modify the list itself. You just want to be able to take that data and apply it to some other task.
So it's side effects.
Right. So you want to do something, but you don't want to remember it. Or maybe, we're going through our bank accounts. We want to send everybody a letter saying your balance is this, but we don't want to change the list. Or maybe we want to figure out what if we changed our interest rate, and sort of calculate something based on that. But we didn't actually want to modify it because we hadn't done that permanently yet. Okay. So let's actually talk about some finite streams. Or let's talk about first how we would define streams, and we'll talk about some finite ones. So I told you at the beginning that con stream is a special form. Con stream takes two elements, A and B. Con stream is equivalent to cons A to the delay of B. This is the first time that we're seeing delay. We haven't seen this before. Delay is also a special form. And if we were to say delay B, this special form is the equivalent of saying lambda of no parameters B. We wrap a lambda around B. We make it a procedure object. We don't apply it. Okay. Why does delay need to be a special form? Why can't I just make it a procedure that wraps a lambda around B? Then it's going to evaluate B and evaluate delay and then apply delay to B, at which point we would have already calculated what we were hoping to delay, which would be a problem. So that's why we need to make it a special form, because special forms have the special rules of evaluation. We won't actually evaluate B. We will just wrap this lambda around it. So we need to have force, which is going to cause a delayed procedure to be evaluated. So if we have force, a delayed proc, what we want to get out of this is what? What do we want force to do? If we've wrapped a lambda of no arguments around B, how do we want to get that B back out? Right. So now what we're going to do is we're just going to apply that delayed procedure. Okay, so we could actually write this out. We can define delay. Actually, we can't. This is a special form. Let's not define delay. But we can define force. So if we want to force D, what's the body here? D in parentheses. Because we're applying at this point the procedure of no arguments that delay created for us. So if we've got this delay here with constream, this is what's going to allow us to create streams that define themselves in terms of themselves, because we can actually, we're not going to compute this until we've already defined some stream already to use. We'll see infinite streams in a little while. Let's just finish talking about delay. If we have stream car of some stream, do I need to change, what is stream car going to be? This is how we build a stream. We cons A to the delay of B. If I want to pick off this A, what code would I write to get that? Car. It's just a list structure. It's just a con cell. The car of S. Okay, so we can just pick off the car of S. It's a con cell, just like all the other con cells that we've seen. The only difference is that the cdr is going to be a procedure object now instead of the actual B, right, that we're wrapping around this procedure. So you can think of this as our stream. This is going to be whatever A was, and then we're going to have, for the second part, some procedure object that has no parameters and the body of B, and this will point up to some environment wherever we evaluated it. Yes?
So force isn't actually evaluating the delayed proc yet, or is it? I'm not sure how to count for it.
So, okay, let's say we have com stream of 1, 2. So this is, and in fact, this is degenerate, right? We're not going to want to con stream 1 and 2 together. We'd want to con stream 1 to the con stream of 2 to the empty stream, right? Because we're going downstream, so we're looking for the empty stream. But for just this example, let's look at something short. So this is going to be is the equivalent of saying cons 1 to the delay of 2. So this is going to build as a con cell where the first is pointing to 1, and the second is pointing to a procedure object which takes no parameters and which body is 2, and this is going to go up to the global environment. All right? So then when we actually go to get the stream cdr, which we haven't written yet, okay. Well, it's the cdr of our stream, right? But what do we need to do to it? We need to evaluate it. We need to force it. We're going to force the cdr of S.
So the only actual special form with special evaluation rules is delay. Everything else is...
Well, no. This is a special form here. We have constream, which is a special form,
Well, I mean,
and delay.
The only thing with special evaluation rules.
No, constream has special evaluation rules. If we didn't designate constream as a special form, this would be evaluated, right?
I'm seeing it as being in terms of being equivalent to...
It's equivalent to, but it needs to be a special form because...
We didn't list any of these as special forms the first day. I don't know if that list was not complete or...
Wasn't complete. It wasn't. Well, we had, I mean, it had cons on it. No, cons isn't a special form, rather. But it did have delay and force, didn't it?
No.
Rather delay. Delay was there. Okay, that list wasn't complete then.
Did you get all 15 of them?
We had 15 of them.
We had 15.
15.
It wasn't complete. Yeah, they tell you there's 15 and then there's more. Yeah, there are more. Delay is a special form. Constream is a special form. But none of these need to be special forms. Force doesn't need to be a special form. It can just be a procedure, right? Because it doesn't. We're taking out a delayed procedure and can evaluate it. It's okay. And these two also. All right. So here's how streams are working, what I'd like to talk about briefly, and that John is going to go over a lot in recitation today, is something called memoization. John's going to go through this with environment diagrams and everything. I know you're very excited. Okay. When we have written streams in this manner, when the stream coulter is defined to be the force of the coulter of S, if we are calculating the same element of the stream a number of times, we're performing additional computation every single time. Every time we ask for an element of the stream, we need to recompute it. And this is incredibly wasteful because once we've computed an element of a stream, why not remember that we did it? Why keep doing it? Sort of like the Fibonacci example from a while back. Right? It was silly to define Fibonacci of n in terms of adding n minus 1 and n minus 2, the Fibonacci of those two numbers, because we found that we were computing things multiple times. The same thing is going to happen with streams if we don't use memoization. Okay? So what memoization turns out to be is that we compute the value if not already computed, otherwise, we're just going to return the computed value, the previously computed value. The way we write memoization, the memo procedure, is as follows. And I promise you this will be going over in detail in recitation today. John's over there going, well. Okay, so memoproc takes in a procedure. And it sets up an environment frame with a let, where there are two variables. One is already run, which will initially be set to false. And the second is result, which is also going to initially be set to be false. And this is going to return a lambda of no arguments, which says if not already run, okay, so if we haven't run it yet, then what do we need to do? If we haven't figured out the value, what do we need to do? Figure the value out. So the way that we're going to do that, so we're going to have a begin. Remember, that's another special form. And what I'm going to do is I'm going to use setBang. Because remember, this procedure is hanging off of this environment containing these variables. So what I want to do is I want to change already run to be true and the result to be what the actual result is. So I'm going to setBang result to be or passing in the procedure. So if I want to get the result of that procedure, evaluating that procedure, I do what? Evaluate the procedure. Now I'm going to say that I've already run it. Set that to be true. And then finally, do I want to return the result of setbangs? No. What should I return here? Should I return already run or should I return result? Result is the better thing to return. Will give us the behavior that we would expect. Finally, our else is going to be if we have already run. If we have already run this procedure, what should we return? Result. We already have an answer. So,
2 points of confusion with that code. Number one is I don't see how that's going to loop. If it doesn't loop somehow, it seems like each time we call it, already run will be set to false. And my second problem with it is it's just looks like it's just going to return a procedure. It's kind of related to the non-looking.
Well, I think the problem that you're having is that I haven't actually rewritten delay to use this. I need to rewrite delay, which of course I erased. So we had said that delay of A, well, that was just lambda no procs A. Okay. Now we're going to be smarter. And we're going to use memoization. And now delay of A, well, that's going to be equivalent to memoproc. So remember, our stream, we cons A to the delay of B. So we're consing the first thing to this, which means when we evaluate memoproc with procedure passing in, we get a let frame that returns a lambda attached to it, and our con cell is going to point to this procedure object. And this is what John is exactly going to do in recitation today, to go through this in a lot of detail about showing exactly how these frames are created, where the procedures are created, and how things are remembered this way. Okay, so he's going to go through that in a lot of detail today. So I wanted to show you guys here, talk about it a little bit, and then there'll be a lot more detail and recitation about it. So you've already seen the idea. You can think about it a little bit over the next few hours, and you'll see it more then.
Does delay actually do this?
Delay actually does this in Scheme.
Does that mean that if you were trying to create a stream to figure out the 40 billionth digit of pi, you would run out of memory because you're still keeping around the state from when you calculated the 43rd?
You might. Yeah.
Isn't this rewriting delay to not be a special form anymore?
Equivalent.
Well, it's equivalent to. I didn't actually define delay here. I said it's equivalent to that. Delay is still a special form. We still need delay to be a special form because we do not want to evaluate this before we walk into here. Huh?
So where's the delay in this system?
So this is delay here is equivalent to. Just like I said, delay here was equivalent to lambda of no arguments A. Delay in our new system is equivalent to saying memoproc lambda no arguments A.
So we can't actually write this function.
You cannot write delay. This is how it works, but you can't write it. You could write memoproc.
Right.
Memoproc is not a special form.
But you can't actually.
You cannot, huh?
You can't use memoproc? I'm confused.
No. We could write memoproc, we could use memoproc. We could not rewrite delay, just like we can't redefine if. We can't redefine delay. You could call it something else and you could try to define it, but it's not going to work right because when you write it yourself, then the normal evaluation rules are going to apply, which means to evaluate a combination, we're going to evaluate the sub-expressions in any order, which means that we will evaluate this expression before we delay it. And that's sort of violating the whole point of doing a delay, right? If we evaluate it and then try to delay it, well, we've already evaluated. What are we delaying? Yeah? Maybe? Okay. So we can't rewrite this. We can't rewrite this, but everything else that we can rewrite. Okay. So delay is going to be smarter in Scheme and is going to do memoproc. And you're right, there could be a problem if we were calculating billions and billions and billions of things. Our memory could die. We could just try to write our code so we were taking streams and trying to get rid of them at certain points and doing all sorts of other things. All right, so that's memoization. And so far, I've been doing lots and lots of hand waving, and we haven't done anything concrete. So let's actually write some streams. Now, there's two types of streams, finite and infinite. Let's first declare a finite stream. Let's have some finite streams. So I could delay a stream that just has a couple of elements in it. So I could define 1, 2 to be con stream 1 to the con stream of 2 to the empty stream. Okay. Notice, just like lists, we want to have the empty stream at the end of it. Just like with a list, when we're making a list, we define 1, 2 to be the list of 1, list of 2, nil. Okay, same thing, yeah.
Is there like a meaningful conceptual reason that there's no equivalent of just saying list for streams, or is that just the way it is?
The reason I think there isn't one is that when we move to infinite streams, we're actually going to see that for the most part, we're basically going to constream two things together. We're going to constream something onto a recursive call of itself. And so that there's not really a point at which we would use something like that. Streams are usually, when we do usually use streams, we're usually going to make them infinite streams. Otherwise, there's not really a great win to this data abstraction if we're using finite streams, right? I mean, we could have them, we could think of some examples maybe where they might be useful. But for the most part, streams are good because they can be an infinite data structure. And Scheme allows us to make this infinite data structure without blowing up the computer, which are good things. So here's a finite stream. What if I wanted to do a stream map of square over 1, 2? What would come back? Well, streams do kind of weird things. The stream, you can think of conceptually, that will be returned is the square of 1 and the square of 2, the stream 1, 4. When streams print out, you're going to get, on our system at least, value. You're going to see a cons pair. 1 dot promise, blah, blah, blah. A delay is a promise. When we delay a procedure, Scheme is promising to do it if we ask for it. Okay, so you'll see it actually prints back promise. Okay, so that's how this particular stream would be done. Now, we wrote a procedure called, print stream, display stream, something with stream. Display stream. So if we were instead to say display stream, stream map, square, 1, 2, that would actually print out 1, 4, value, done. The base case on display stream just returns done. Say we're done. Because if we didn't have a value return, we'd get an unspecified return value. It's sort of messy, nasty Scheme. So we just put this done in display stream to give that. So if we just map it, we get back the stream, which we could then define to be some other thing. Define square 1, 2. Or we could just display our stream, our results here. Remember, just want to say it again, we're using display stream. It's fine because we have a finite stream. Just don't go there with infinite streams. So that's our finite streams only. So we could actually write a procedure to it and basically create a finite stream for us that enumerates a particular interval. Let's say we wanted to have a stream be all the numbers from 1 to 100. Well, I certainly don't want to write constream 1, constream 2, constream 3, constream 4, 5, et cetera, et cetera, et cetera, especially since we know how to write procedures to do that. So we could define, I could find my sheet, stream enumerate. Interval. And we're going to enumerate interval from some low value to some high value. Okay. So we're going to count up. You could write some procedure that would count down. This one is going to count up. So if we ask it to enumerate the interval from 1 to 100, we'll return the stream 1, 2, 3, 4, dot, 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 up to 100. So how would we write this particular procedure? What's our base case? When do we not do anything? If low is bigger than high. So if low is bigger than high, what should I return? Empty stream. Otherwise, what do I want to do? I need to start building up my stream, or continue building it up before a recursive call. So we're going to con stream. What should be the first element of our stream or our substream we're on right now? Low. And what will the rest of the elements of the stream be? Recursive call to stream enumerate values, enumerate interval. What happens to low? We increment it. Do I do anything to high? Don't need to. Just keep it. Okay, so the example I've been giving is if we want 1 to 100, so I could define stream 1 to 100 as what call? Right. Stream enumerate interval 1, 100. So that would allow us to create some finite streams. And then if we wanted this to perhaps be all the odd numbers between 1 and 200, if we want to create that stream, what would we do?
The low is odd. If the low is odd, it's odd.
2n minus 1.
Okay. So we hear 2n minus 1. So we could define odds 1 to, actually it won't be 200, but let's say 200. So 1 to 199. And here we can use our stream map procedure. Lambda n. And Sam says 2 times n minus 1. So for the first one, that would be 1 times 2. 2 minus 1, 1. Ending case, 100 times 2 is 200 minus 1, 199. Do people believe me that it'll be the same throughout the middle cases? Or we could just stand here and I could just talk for the next 5 minutes. So we're going to map that over what? S1 to 100. Okay. So we can create finite streams. We can map stuff over them. We could write stream filter. We can do all the sorts of things that we could do with lists. Yes?
In the original stream enumerate interval, why, when we say const stream low, are we counting the actual value passed in as low?
Yes.
Or, so we don't want the element at the low element, the element at. Like we pass in 5, don't we, as low, don't we actually want the 5th element?
No, this is just, when it's enumerating an interval of numbers.
Okay.
So if we say 5, 20, it'll be the numbers between 5 and 20. It's not picking out elements out of every stream,
Okay.
or any stream rather. It's pure numbers, 5 to 20, 1 to 100, 1,000 to 8,000, some interval where we're going to add 1 and count up.
Couldn't we equally well say define odds 1 to 200?
Sure. If you'd prefer, we could say odds 1 to 200.
No, I had said it originally and you changed it to 199.
Oh, I just changed it to 199 because they're odds, and yeah, it's all the odds 1 to 200 or 1 to 199 or whatever we want to name it. Okay, finite streams. Not very exciting. They're lists with some delay. So let's go to the fun and exciting stuff. Let's do some infinite streams.
I have one question. Is stream enumerate interval a primitive, or is that just a procedure we define?
It's a procedure we define, and I don't believe it's primitive. Okay, so infinite streams. Let me define a stream of an infinite series of ones. I will call this stream ones. I will define this to be the con stream of 1, 2 ones. I have now defined an infinite series of ones. That's cool. Come on, that's pretty cool. And why can we do that? Because this is delayed. If constream were not a special form, we would blow up. We would get into the happy little debugger, which is not so happy, but it would tell us we'd have a problem because we hadn't yet defined this when we're trying to use it over here if we didn't have a special form for constream. So ones will be the stream. Well, this will actually return ones, which is map to 1 dot promise, blah, blah, blah. Okay, but we can think of it. What I'm going to do now is just sort of, yes?
I see how. Why? Why do you want to do that?
Because we can is not the answer. Why is that? What we can do with infinite streams is we can represent some sort of time series that's going on. So it can represent something happening over time, where when we're at the beginning steps, we don't know what's going to happen in the future. We can calculate that as we go along, and we can have a program that runs off doing stuff into the future in sort of infinite sort of bound. And we don't know where we're going to end running our program, and this is going to allow us to represent something like that.
You can also evaluate infinite series.
Yes. And we'll use power series on the next problem set. So. Huh?
First time this month.
Okay. So now we have infinite streams. So ones you can think of as the stream 1. Well, that's cons to ones, which right now is the stream 1. So then this one goes here, basically builds it up. Actually, let's write it this way. It'll be a little bit easier. Here we go. Here's ones. Well, ones is a result of con streaming 1 onto ones. Well, that's 1, 1, 1, 1. Yeah, this is fun. Bye. Okay. So, that's a pretty simple example. It's a big, long stream. So that's ones. How would we define an infinite stream of zeros? Exactly. So we define zeros to be the con stream 0 to zeros. Okay. Some sort of pattern here, right?
It's actually just 2 con cells. The
second one is a promise. It's just a procedure. It's a procedure. So this is going to be a con cell of 0 to some procedure that takes no parameters, whose body is zeros. That goes up to the global environment. Okay, so that's what zeros is when we build it up. Now, as we continue to evaluate elements of zeros, what we're going to get is some list structure coming up. It's going to con some stuff out, and we'll have memoized procedures. Right? So actually, I say this is going to the global environment. This is actually going to the let box for memoization if we're using memoization. And the let box goes to the global environment. And that will be an environment diagram that you're going to see today in recitation. Okay. So far, we have very little that we can do with infinite streams. So let's define some streams, procedures for infinite streams. Let's write add streams of S1 and S2. And let's assume that they are both infinite streams. So no checking for null stream or stream null. So if we're going to add 2 streams, what do we want to do? Term by term. And we want to return, what are we returning from this? we're returning a stream. So we're going to const stream with the first element being, well, I've got stream car. We want to add the two cars, right? I want to add two streams. So if I had zeros and ones, not a very exciting example, I would get ones back. But let's say I were adding ones to ones, then I could get the stream twos back. Okay, so we're going to add the elements of two streams, going cars of each matching up. So we're going to add the stream car of S1 to the stream car of S2. And that's going to be const to what?
Add stream.
Right. Add streams of the stream cooter of S1 to the stream cooter of S2. So, now that we've got add stream, which we've assumed is only going to be for infinite streams, how can we use it? Well, let's define twos like I did over there. So how could we define twos? Well, we could do it the same way, but let's say we have to use add streams. You're going to add streams ones and ones.
1 plus 1.
It's Monday morning, you know. Yeah, we're going to add 1 to 1 to get 2.
That's right.
Okay, so now we've got ones and ones. Now, what if I wanted to get odds? Sure.
What will that return? Will that return the numbers or promise?
What this will do is it's going to actually compute the first element, and the rest will be a promise.
Okay.
So we'll get 2 promise, blah, blah, blah. And actually, this is going to return some unspecified value, which in our system will be 2 pointing to 2 promise, blah, blah, blah. So odds, I would like to claim, I could define as following. I take a 1. Then what I could do is I could take the odds and add it to the stream of 2s. Yes.
Use the odds to calculate odds.
Yes, I did. Just like we just use zeros to define zeros.
Oh, I get it.
Right? I think that was I like it. Yes, you could use odds to define odds. Huh?
That was a breakthrough, right?
That was a breakthrough. All right, so how would I write code to do this? Now this nice little one line here is my way of saying I'm const streaming 1 onto something. I'm going to const stream 1 to the result of what? Yep. Add stream 2's odds. Cool, huh? And again, we can do this because the streams are delayed. And that buys us this. So now we can define all sorts of other things. Let's define some integers. Can I erase add streams? Okay, so what I'd like to do is define integers, and I'm going to call, that's going to be my stream of non-zero positive integers or positive integers, 1, 2, 3, et cetera, et cetera, et cetera. So how could I do that? I hear const stream 1 and up. I hear con stream 1. Okay.
Stream.
Add streams. Ones and integers. Let's draw this out. So we have integers, which is defined as 1, cons to the result of adding ones and integers. Well, the first integer is 1. The first one is ones. 2. That's the next integer. The next one is 1. 3 is the next integer. Next one. 4. Okay, so we've just defined 1, 2, 3 in terms of adding ones to integers. But of course, we could do this other ways. Here's another way to do it. What I'm going to do is I'm going to add 2 streams. Where the first stream is going to be 0 constreamed to integers, and the second is going to be ones. See how this works. Okay, so I got integers. Oops. Okay, and I'm going to add 2 streams. I'm adding ones, and then I'm adding the con stream of 0 to integers, which means that this first element is a 0. First element is a 1, giving me 1. Well, I con stream 0 onto the integers, so that's now 1. That's 1, 2, 3, 4. 4 plus 1 is 5. Okay.
But that's essentially the same as above.
Hmm?
But that's essentially the same as above.
They're all coming out with the same results.
Yes, but the save for the 0 plus 1 is exactly the same.
Here we're consing a 1 on at the beginning. Here we're consing a 0 onto result and actually adding these two. It's a slightly different representation of it. Comes out with the same sort of thing. Doesn't only have to be one way is the whole point here. So I brought up Fibonacci a little bit before. Fib n equals to fib n minus 1 plus fib n minus 2. You guys remember Fibonacci numbers? How could you forget this lovely recursive example? Okay, so let's define a stream. And of course, fib of 0 is 1, and fib of 1 is 1. We need some sort of base cases. So I can define a stream called fib. Okay, so I know that 0 and 1 are 1 and 1. So what I can do is I can do a con stream 1 to a con stream 1. They're my first 2 elements. What are the rest of my elements going to be? Some of the previous 2. But what I need to get is, here's fib 1, 1. What I want to do is my next element needs to be, what I want to do is I would add 1 to 1 to get 2. But then I want to add 2 to 1 to get 3. Then I want 3 to 2 to get 5. I want 5 to 3 to get 8. 8 to 5 to get 13. So I'm adding 2 streams. What's this stream? And the stream above it is the Kutter fib. Stream Kutter fib. So I can constream 1 to the constream of 1 to add streams fib to the stream Kutter of fib. I have enough now. That's Monday morning matching. I've matched enough. There's extra credit parentheses. Okay, so that's one way to define Fibonacci. And because we have memoization, we're not recomputing anything. So here's a nice, neat, easy way to compute Fibonacci numbers. Okay, so let's look at showed you guys add stream. What I'd like to show you guys is a print stream, which I actually wrote out for you guys in the code handout. The problem set calls it show series because we're talking about infinite series. But this is, if you want to start printing out streams, you'll need to have a procedure like this. Define print stream. It's at the top of page 3, which takes in a stream and a number of elements that we wish to print. Okay. I'm going to check for the null stream just in case we pass this a finite stream, in which case I can return the empty stream. If we've hit 0, I'm going to return the value done. I'm done printing. Otherwise, I'm going to use display line from our first page, stream carve s, and then I'm going to call print stream on the cdr with n decremented. So this is a handy procedure. I've been cut out. Oh dear. Alex is putting paper up instead of me. This is like the episode of The Real World where I'm not exciting enough to even make it. Okay, so this is a nice, convenient procedure for printing out the first n elements of a stream. So if you guys are playing with streams and you want to see what the elements are to see if it looks like the series you're actually hoping to create, this could be something convenient for you. Or you could use streamref to get the nth element. If you know what the nth element is going to be, you can check it that way. A couple of different ways that you guys can look at your streams. Okay, what if I wanted to write a procedure to scale a stream by some factor? Well, we could use stream map, or we could just write something sort of like add streams, in which we would con stream. What would be the car? Yeah. Stream car S. Oops. To what? Of the stream cdr. To with rather factor. Okay. So now we can scale a stream. You can write subtract streams, negate streams, all sorts of other stream procedures like that.
Why wouldn't you just use that stream?
We could. How would we write it using map? So now we're going to call stream map, which takes a procedure. And we're going to map that over S. Perfectly acceptable. Either way, fine. Questions? Okay, let me write another procedure. If you haven't learned by now, the absence of questions means more material. Which is why I know you guys ask a lot of questions.
What's the airspeed of an unladen swallow?
Excuse me? I hear swallow. I'm like,
No, the airspeed of an unladen.
oh, the airspeed of a swallow. Excuse me. I'm afraid I can't answer either of those questions. I'm going to define another procedure called partial sums. And take in a stream. And what I want partial sums to be is to be S0, and then S0 plus S1, S0 plus S1 plus S2, S0 plus S1 plus S2 plus S3, et cetera, et cetera, et cetera. So, how do I define this? Well, what's my first element of partial sums? Right. So I'm going to constream the stream car of S to what? Let's actually look at an example. Let's say that we're going to do partial sums on integers. Okay. So I'm going to have the first integer is 1, and that's going to be cons to something. Okay. Drew a nice little line for addition, maybe.
Now I'm confused. What is the partial sum supposed to calculate? Is it supposed to calculate the sum of?
So if we have, let's say we have integers. So this is going to be 1, then 1 plus 2, 3, 1 plus 2 plus 3, 6.
Right, so it doesn't add them up.
Okay.
Right,
So
it doesn't accumulate them, right? It doesn't create calculate the sum.
I'd like to make the observation that this is partial sums on integers, and this is integers. One plus 2 is 3. 3 plus 3 is 6. 4 plus 6, 10. 10 plus 5, 15. So how would I write this?
Add stream integers.
I want partial sums of what? Do I want the car, or do I just want partial sum ints?
Partial sums is.
Or which would be partial sums S, right? Because we're writing a procedure to do this. Right? This was just an example where I substituted in ints for S. And we're going to add that to what? Right. This is the coulter of S. I'm missing what? No. So if we were now to call partial sums with the integers and evaluate that with print stream, perhaps for the 5 first elements, it would return 1, 3, 6, 10, 15. Done. Check. 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 Questions? There's one more page of the lecture handouts. It talks about merging 2 streams. It talks about the following problem. So there was a problem first raised by Hemming to enumerate in ascending order with no repetitions all positive integers with no prime factors other than 2, 3, and 5. Okay. So let's make some observations. Let's call this H. What number are we going to, what is our stream going to start with? 1. So other elements of H, right? Scale stream H2, all elements of H. Okay, so any number in H that we multiply by 2 is going to have no prime factors other than 2, 3, and 5. Similarly, any number in our stream H that we multiply by 3 or 5 is going to have no factors other than 2, 3, and 5. Okay, so these are elements of H. So let me tell you that on that page we have written a merge streams, or streams merge, just merge. We've taken two streams, S1 and S2. And it's going to return a stream. Let me also tell you that these are assumed to be in ascending order. Okay, so we're assuming that they're going up. So S1 might be the integers 1, 2, 3, 4, 5. S2 might be the odds 1, 3, 5, 7, 9. But they have to be going up in order. So we're going to return a stream which will be in ascending order, because the two streams are merging, we're in ascending order, with no duplicates. So a little bit of talking about the pseudocode. You actually have the code in front of you. I don't want to write it on the board because we don't have enough time for that. Basically, what merge is going to do is it's going to look at the car of S1 and S2. If S1 is smaller, it will put that in as the next element of the stream and recurse. If the car of S2 is smaller, it puts that in as the next element of the stream and recurses. If the elements are the same, it will put one in it, one of the two elements in, and recurse on both of the cooters. Check? Okay.
If they're the same, it puts them.
It puts one in. Okay, so given that we have merge, how could we write H? What's the first thing? What's the first element of our stream? 1. Good, that's the easy part. So now we want to do some merging. Merge only takes 2 arguments in. I need to call it twice. So let's merge this with the merge of this. We're going to merge scale stream H2 with the merge of scale stream H3 with scale stream H5. 1, 2. And that will return the stream of numbers of this property. You guys can type it in and play with it. Why? Because we can. Because it was time to get back to some math examples for Sam.
Well, I give you a problem.
Oh no, don't give me a problem. On that note, if there aren't any questions.